In this video, we're going to explore inscribed angles in a circle and a couple different sketches related to those. The first one is just what a basic inscribed angle is. So here we have what's called a central angle. The vertex of the circle is at the center of the circle. So this is circle A. And you can tell here we have that defined measurement of 108.91. We also have the measure of an arc here, arc BD. So happens to be the same as the central angle. We'll explore more of that later. Then we have this inscribed angle. Now, an inscribed angle will take the same points, B and D, but the vertex is not at the center of the circle. The vertex is actually now at any point that's on the circle itself. So what ends up happening here is that we can take this point C and we can move it anywhere as long as it's outside those points. And you can tell that measurement is not going to change. I can change some things about the central angle, and as I do that, angle C is going to change as well. You may have noticed that angle C, so angle DBC, BCD, whatever you want to call it, or just angle C, is 1/2 of this central angle, which is also the measure of the arc. So an inscribed angle, and this is a little theorem that we've got, an inscribed angle will be half the measure of the arc that it cuts off. So let's put that into practice. Let's do some problems here relating to that. So if we want to find the measure of arc AC, we know that this angle right here, this 42, is the inscribed angle. So I can highlight that guy right there. And I notice that when that cuts off this arc, that inscribed angle is supposed to be half that arc. So if I want to find the arc, I just double it. Oops, I didn't grab my marker. There we go. Double the 42 to get 84 degrees. Versus the next one where I have the measure of the arc and I want the angle. So in this case, I'm going to divide the arc by 2 to get the angle. So half of 92 is 46. And I can set up some algebra problems involving the same thing. Like I could take this one here. If I'm looking for angle O, I know angle O is going to be half of this arc, because again, here's my cutoff. So if I double my inscribed angle, I should get my arc. And then we can solve from there and plug it back in. That's nothing relatively earth-shattering there. But we're going to look at some more sketches related to inscribed angles. So in this second sketch, we have a diagram here where we've got a circle, go figure, in this entire chapter here. We have our arc BD, which is 109.92, and again I can move some things around to change it if I want to. I'm going to highlight my first inscribed angle, which would be this guy right here. I can move my point around if I want to, and again, doesn't change the measure of the arc, or so the angle. If I take another inscribed angle using those same points, I get the same measure. And I gotta be honest, I think that makes intuitive sense because we're going to take a look at this arc here, and we know that an inscribed angle is half the arc. It doesn't matter where that arc hits the circle, as long as it does, this inscribed angle. It is cutting off the same points, which are points D and B. So, believe it or not, that's a theorem in geometry that if we have an inscribed angle or two inscribed angles coming from the same point, then they're going to be congruent. So let's put it into practice with a problem like this. We want to find the measure of angle HIP. So highlighting this guy right here. And you can tell from the way we've highlighted that it's going to cut off this arc PH. Well, I do know the measure of angle C is 46, so let's see what happens when I highlight that one. Turns out that they're going to cross the same points at H and P. So if I wanted to, I can go through the process of saying, okay, well, this is 46, and then the arc will be double that, and I cut it in half, or they intercept the same arc, so they have to be congruent. Angle HIP has to be 46. And I can do that when I'm solving for algebra as well. So if I'm looking at angle P and angle L, both of those cut off arc YA, and so therefore they must be congruent. So I can set up an equation to solve for x. 3x plus 27 equals 6x minus 3. And then I can solve for x. I'm going to bring the 3x over and add the 3 over to the other side. So 30 equals 3x. X is 10. So that makes this 6 times 10, which is 60 minus 3 is 57 degrees. If I want to find YA, that's going to be double that. So if I take 57 and I double it, I get 114. So that's how we're going to potentially use that idea of inscribed angles intersecting the same arc must be congruent. And in our next sketch, what we're going to take a look at here is an inscribed angle of a semicircle. So here we're going to have these arcs, and we have a semicircle right here. So we want to basically take this and move it so that we get down to 180 so that it's lined up perfectly. And when we do that, there we go, that inscribed angle C, no matter where I put that on this the edge of the circle, it's always going to be half of 180. So when I have 180 degrees and I take half of that, I'm always going to get 90 degrees. Again, pretty intuitive that if you've got a semicircle and the inscribed angle is half of that, then it has to be 90 degrees. It has to be a right angle. So let's put that into practice. So here we want to find the measure of segment SE. Notice that's a segment versus an angle. So what I notice about this one is that this segment right here, TE, is a diameter. And the fact that it's a diameter tells me that I've got a semicircle going on. If I'm looking at angle S and I were to highlight that one, angle S cuts off the same points as that diameter does, which tells me then that is an inscribed angle on a semicircle. So if I know I've got 180 degrees here, then this will equal 90 degrees. So I can set up x squared minus x equals 90. And this is where it gets a little bit tricky because I want to find out what x is. So I can bring x over to the other side. Or sorry, the 90 over to the other side, and then solve for x. And then to solve for x, what I'm going to do is factor. So I've got x squared minus x minus 90. I believe that's going to be x minus 10. And x plus 9 equals 0. So then x potentially equals 10 or negative 9. Negative 9 won't work because if I plug it into either one of those segments, I'm going to have negative segment measures, and that's not a good situation. So I'm going to plug that 10 in, and when I do, I'm going to get a 25 here for the diameter, and I'm going to get a 7 for ST. Well, that forms a right triangle, and a 7 and 25, my remaining piece is part of a triple, and so it's 24 for that missing side. And our last sketch, we are going to take a look at what's called a cyclic quadrilateral. First, we need to define what a cyclic quadrilateral is. So let's click that button and see. And it looks like all of the corners of this are part of inscribed angles. So every single vertex, every single corner that we have is actually on the circle itself. No matter where I move, it's still going to be the same. We've got our cyclic quadrilateral. So let's pull up the angles then. So really want to focus on the green ones and the blue ones. So the green ones here, I've got a 79 degree angle and a 101. Clearly those are not the same. But if I would look at other relationships, it appears that maybe, it could be wrong, I don't know, but it looks like those add up to 180 degrees. And if I look at the blue angles, that appears to be the same. So if I have 110 and 70, that's 180. If I move that point D around to other places, that's still going to hold true. So if I drag this around, the green ones change, but they still add up to 180. So in a cyclic quadrilateral, the opposite angles are supplementary. So how would we use this in a problem? Well, if we wanted to find the measure of angle L, in order to do that, we have to find the measure of angle S. But to find that, we also need to find out what x equals. So what I'm going to do is set these two angles, x squared plus 3x plus 12, and 9x plus 8. I'm going to add those up to 180. and then I can solve from there. So I'm going to combine like terms. I've got x squared plus 12x plus 20 equals 180. And then I can bring the 180, x squared plus 12x minus 160 equals 0. So that would become x plus 20 and x minus 8 equals 0. So x could be negative 20, although unlikely, or x could be 8. Negative 20 is not going to work, so I plug that into basically anywhere. It's just not going to work. And I can plug 8 in, and it will. So if I'm going to find L, I want to plug that in for S. 10 times 8 is 80. Take away 5, I get 75 degrees. And then angle L is the supplement to that. So 180 minus 75 is 105. Oops. Try that again. 105 degrees. Okay? So again, inscribed angles, half the arc, and then we have all those different relationships related to those inscribed angles.